Okay, today we're going to work on homework week 5, which is fluid dynamics, or and there are some medical applications to this as well that we'll be working on. The first problem we're going to do is problem number 6. Problem number 6 states a major artery with a cross-sectional area of 1 square centimeter branches into 18 smaller branches, each with an average cross-sectional area of 0.4 square centimeters. By what factor is the average velocity of the blood reduced when it passes into these branches? Well, we know that the area times the velocity is going to equal the area times the velocity. And so we also know that this is going to be 1.0 times the first velocity is equal to 18 times 0.4 times the second velocity. Now, if the question is, what is the ratio of these two velocities, then that means we're going to divide 1.0 by 18 times 0.4, which equals 0.139. So the velocity decreases by a factor of 0.139. So, for example, if the first velocity is 1, the second velocity would be 0.139. If it's 2, it'd be 2 times 0.139, and so forth. The next problem is problem number 9. Problem number 9 states, estimate the time it would take to fill a private swimming pool with a capacity of 80,000 liters using a garden hose which delivers 60 liters per minute. Well, you have 80,000 liters, and it's going to be filled at a rate of 60 liters per minute. And if you do that, you get 1,333 minutes, or approximately 22.2 hours. Now that's part A. Part B says if you have the same pool and it's being filled by diverting a moderate-sized river which flows at 5,000 cubic meters per second, well, the second one you have to work out. You have 80,000 liters, and now you're going to fill it up. You have 1 times 10 to the minus 3 cubic meters in a liter, and then this is flowing at 5,000 meters cubed per second. So it's going to take a grand total of 0.016 seconds to fill the same pool up if you use this river. Number 10. Number 10 states that the flow rate of blood through a 2 times 10 to the minus 6 millimeter radius capillary is 3.8 times 10 to the minus, it's supposed to be a minus 9. The answer book shows that it's a minus 9. 10 to the minus 9 cubic centimeters per second. What is the speed of the blood flow? Okay, so we have the radius is equal to 2.0 times 10 to the minus 6. And the flow rate is going to be 3.80 times 10 to the minus 9 cubic centimeters per second. And so if we take that, I'm sorry, this is meters. We have to change one of these two to a corresponding, and I decided to change the flow rate. So 3.8 times 10 to the minus 9 cubic meters per second. And we have 10 or 100 centimeters in a meter, and we're going to cube that to get a cubic meter. And that comes out to 3.80 times 10 to the minus 15 meters cubed per second. Q, or rate, is equal to, flow rate is equal to V times the cross-sectional area. So V is going to equal to Q divided by A. So this is going to be 3.80 times 10 to the minus 15 divided by pi times 2.0 times 10 to the minus 6 squared. And if you do the math here, you get 3.02 times 10 to the minus 4 meters per second. And if you did it in centimeters, you should get 0.0302 centimeters per second. The next problem is problem number 12. Problem number 12 states that we have a main air uptake duct of forced air heater is 0.300 meters in diameter. What is the average speed of the air in the duct if it carries a volume equal to that of the house's interior every 15 minutes? The inside volume of the house is equivalent to a rectangle solid 13 meters by 20 meters by 2.75 meters. Now the first thing I did here was to calculate the size of the room. So if we take 13 times 20 times 2.75, we get a cubic volume of 715 meters cubed. The second thing I did was to take the diameter, which is 0.300 meters, change that to a radius, 0.150 meters. And the time here is 15 minutes. And so if we take 715 divided by 15 minutes, that means it's going to be 47.7 cubic meters per minute, or 0.794 cubic meters per second. So that's your flow rate. That's going to equal Q. The area based on this radius, pi r squared, is going to be 0.0707 meters squared. And so the velocity is going to equal to 0.794 divided by 0.0707. And that's going to equal 11.2 meters per second. And that's the velocity. Moving right along, the next problem we're going to do, and now we're moving from flow rate and velocity, we're now going to move to Bernoulli's equation. And Bernoulli's equation is P1 plus 1/2 rho V squared, and rho being the density of the fluid or material, and V1 being the flow rate of the material, plus rho GH1 is equal to P2 plus 1/2 rho V2 squared plus rho GH2. Now this equation basically allows you to go from one state, which is this state of conditions, to a second state. But many times several of these factors drop out because they either do not change or they're not relevant. So let's take a look at the first problem, problem number 19. It says if the pressure reading on a Pitot tube is 15 millimeters of mercury, so P1 is equal to 15 millimeters of mercury, at a velocity of 200 kilometers per hour, what will it be at 700 kilometers an hour at the same altitude? Now this is pretty simple. So if you take this basically you can eliminate this because it's at the same altitude. So H1 is equal to H2, and this factor doesn't come into play. And so the question is, you know P1, you know everything here except for P2. So if we solve this equation for P2, P2 is going to equal to P1 minus, well, let's say plus 1/2 rho V1 squared minus 1/2 rho V2 squared. So P1, and it's going to be plus 1/2 rho times V1 squared minus V2 squared. And so let's calculate what these entities are in units that we can use. First of all, 1 millimeter of mercury is the same as 133 newtons per meter squared. I just looked that up in the chapter. And so if we take that times 15, we get a new pressure value. And that pressure value is going to be 1995 newtons per square meter. If we change these two velocities to meters per second squared, this velocity equals 55.6 meters per second squared. Multiply by 1,000, divide by 3,600 in both of these. And this velocity is going to equal 194.4 meters per second squared. So now we can put all this in here. This is going to equal 1995 plus 1/2. And they don't tell you here, but the answer book uses the density of air, which is 1.29 meters squared kilograms per meter cubed. And they don't really tell you you're using air, but you have to kind of figure that out. And then it's going to be V2 squared, 55.6 squared, minus 194.4 squared. And then if you do the math here, you get minus 2.04 times 10 to the minus 4 to the fourth newtons per meter squared. Or minus, if you divide this by 1.01 times 10 to the minus 5, which is atmospheric, which is a Pascal, it's minus 0.202 pascals. If you change it back into this millimeters of mercury, it would be minus 153 millimeters of mercury. So when you speed up the air with nothing else happening, you develop a negative pressure, which is how many of these situations work in order to cause fluid to go up into a tube or things of that nature. All right, let's stop at this point and we'll continue with this discussion and also answer some of the questions on the next